The next presentation is about manufacturing a dielectric material which effectively can provide good insulation, minimize the losses during the dielectric leakage and it can be used for many applications. It can be used for electrical insulations, it can be used for capacitor insulation between the charges, the charge plates, etc. The content of the presentation will be a brief introduction, the materials and methods to show what has been used in the lab, the results, and the conclusion and discussions. This has been carried out by my colleagues in Cluj University in Napoca, Romania. And so the fabrication, effectively what we have done is that we have tried to implement this dielectric to manufacture it in the lab. And it consisted of glass fiber and of epoxy resin. This the process made for the manufacturing is described with the different let's say details in the paper, and it consists of two stages. One of them was the hand layup, and the other one was when you have to put it in the oven. Yes, and the resulting material was then tested with 4 different parameters. Obviously, according to how thick you make the material, it will have different parameters, and this is what we have tried to investigate. We have 4 test cases. The main deviation between the 4 test cases is that the thickness of the material, we have 0.8, 0.91, and 1.2. We see that for the 3 ABC case types, 3 layers were used. In the 4th one, we had 4 layers used in order to achieve the specific requirements. Now, the test case, let's say the experimental stand, is shown on the left, and that's the electrical scheme for determining the dielectric permittivity of the material and the loss factor of the electrical insulating materials at various frequencies. So effectively, we have that, changed the frequency, and observed how the developed material resulted and behaved during the operation and the losses. And now, starting with the first one, which was with a 0.8 millimeter gap, we see that according to the frequency starting from 400 going to 10K, that's the resulting parameters. With obviously, I'm not going to go reading the tables for each one, but I would like to show the resulting plot for that, about the variation of the dielectric permittivity and the tangent of the loss angle with the variation of frequency. We see that there is a vast increment with regards to the frequency increment, also to the loss angle of this case. Now, obviously, this when we first did this, we thought, okay, this doesn't look very promising. But then, following the next with the increase of the dielectric to 1 millimeter, we saw that things started to stabilize, and we started getting better results, which effectively resulted to a smaller variation of the loss angle and less variation in terms of peaks into the permittivity of the material. Then obviously we had the 0.9, as we said, again with the results that those peaks at the beginning of the loss angle graph according to the frequency, this is something that obviously we didn't want to have. So we ended up having the variation of the tangent of the loss angle when it was 1.2. We see that this resulted to a more let's say, square characteristic of the curve. So it is also more predictable for the application. Now, regarding to the dielectric permittivity, we have on the interval 400 Hz to 1 kHz, which was a sample. In all 4 cases, we had a non-uniform variation of the permittivity, namely at 400, 450, 650, and 950 Hz. Starting from the value of 1 kHz, the variation is similar for all 4 samples, with the exception of the one that we had, E4, which was the 1.2, yes, where the permittivity decreases from 750 Hz. From the value of 5 kHz, the variations of dielectric permittivity with frequency largely overlap. And now with regards to the loss angle, non-uniform variation up to 950 Hz. We have various maxima in the obtained graphs. Constant and similar relative increase of the dielectric permittivity for the samples of 2, 3, and 4, and a non-typical variation of the permittivity for the sample of E1. So as a result, some advantages can be concluded from the particular experimental manufactured materials, the dielectrics, but in combination the cost of the dielectric decreases. It can be cast in different shapes. It can be modeled very easily, has a good mechanical resistance, can be used in numerous applications, and the temperature up to which it can be used, it can reach 200 degrees Celsius. So effectively, what we have done here is that rather than having one of those materials to create the dielectric, we have implemented 2 different materials in order to construct a new dielectric material that has those benefits. And I'm not going to read through that's part of the paper, consisting that the loss factor, the loss angle, gives a measure of losses in dielectrics based on the results obtained. As we have said, the sample E1 is the most disadvantageous, with the other 3 having a very similar behavior in the same applied electric field. Thank you very much. I have included the contacts of my colleague Antoniu, who actually carried out the experimental work, in case anyone is interested to further discuss with them. Yes, any questions, please?
I have a question. So can you give us an example or 2 of the practical application of this material in industry?
Yes. For example, you can use it, the simplest application, the most applicable, is for capacitor dielectric material. Mm-hmm. So when you have the plates of the capacitor, obviously you have the loss, which there's a discharge according to the dielectric material, and the voltage level, which is between the 2 plates. Obviously, when we implement a new dielectric material, then it can provide higher electrical insulating capabilities in order to restrict this transfer of electrons between the plates during the non-charging and non-discharging state.